Before we get into the fourth assumption, we'll kind of summarize these three to see what we have as starting point before we get on to the fourth assumption, right? So we said that there is a tensorial way of writing this equation, and then a matrix way of writing it as well. And once you have the matrix, then there are measure numbers of that. So it's for the measure numbers that we wrote this particular equation for ijkl equal to 1 to 3. So now we are at this stage. Now we still have this in the form of a matrix equation. So that is, you have your sigma is defined as sigma 1 1 2 2 3 3. So the last of the assumptions showed us this is symmetric, and we said that even before we started any of those three assumptions, from the very definition you have the gamma is also symmetric. So this is directly coming from the tensorial equations and the three assumptions that we have made. But now there is a slight difference between how engineers deal with strain and how mathematicians deal with strain, especially when it goes to the shear strains. And we engineers tend to take a right angle within the structure and see how much that right angle changes by overall. So that, let's say if this is delta theta and this is another delta theta, so it's the twice that delta theta that we are looking at. Of course, both those rotations can be by different amounts, let's say theta 1 and theta 2. Now it's the sum of that which engineers say is the shear strain. In other words, it's the change in the right angle that we are talking about. Okay, it could be increase or decrease, depending on that. The sign, of course, gets into picture, right? Now, on the other hand, the way it is taken in the tensorial notation is the average of these two. So, in other words, it's the average rotation that is actually taking place that we take into account in the tensorial notation. So, if we want to use engineering strains, then we typically have to have double the tensorial strain, because the tensorial strain is the sum of, the engineering strain is the sum of this, whereas the tensorial is the average of this. So which case we introduce a factor of 2 only for the shear strains over here. Okay, so it's just a matter of convention or notation. There's nothing sacrosanct about this. It's just has been the way in which we deal with. It's easy for us as engineers to visualize what happens when the right angle changes, how much has it changed by, whereas mathematically you're talking about the average change, average rotation that is taking place, which is why that is there. But the advantage of going for the without the 2's is that then it is amenable to all the typical tensorial manipulation and rules and laws and features of tensors. So you can actually utilize that, which we do in the case of the stress. Similar kind of thing can be done with the strain. But this is how historically we have got, and so we will stick to this particular notation. So once again, by definition, so this is because no body moments. So your mi equal to 0. So in the example that we showed the derivation for, we showed only m3 equal to 0. Okay, so that only talked to you about sigma 1 2 being equal to sigma 2 1. But now we have taken the entire matrix symmetric, which means you have taken m1 and m2 also equal to 0. There is no body moment distribution. in the other two directions as well, okay, along the B1 and B2 directions. So when all the mi's are equal to 0, I equal to 1 to 3, then you end up with that as symmetric, whereas this, as we said, is by definition. Okay. So now instead of continuing to write in this long format, we want to get rid of this fourth order tensor because we can't actually visualize that. At the most we can go up to a second order tensor. Once we have chosen the two bases for it, we can put it in the form of a matrix like we have done for sigma and gamma over here. But whether it's third or fourth order tensor like this, then it becomes a little difficult to visualize how you actually want to put it on paper, right? Because you have four different things changing, so you don't know how exactly to portray it. At the most, we can think of a block for a third order tensor. We can think of the depth as well, but it's like a let's say like a Rubik's cube. So you have all three dimensions that you can take care of. But here it's a fourth order tensor, and therefore it becomes much more difficult. But now we will take advantage of the fact that the quantities that it is relating are both symmetric quantities, and therefore you don't need to deal with 9 quantities, you need to deal with only 6 quantities, right? So we bring in another, you remember we talked about Voigt earlier in the case of isostrain. The same person now comes with a new notation where it's not a mathematically strict notation, but it's very useful for engineers to kind of visualize. What he did is he went along this diagonal, principal diagonal, sigma 1 1, next sigma 2 2, next sigma 3 3. Then he goes around sigma 2 3, sigma 1 3, sigma 1 2. Okay, so he goes in this order, and instead of a 3 by 3 square matrix, he writes that in the form of just use the same symbol, but not supposed to really write the same symbol, but hereafter we will not call this as sigma, we will call this as sigma, and this will be written in that order as a column matrix now. So for the shear stresses, we can interchangeably use sigma or tau. So to just to differentiate them, we look at it as tau over here. So now this contains pretty much the same or all required information as is contained in the original representation, which is much more mathematically acceptable compared to this. But having it in this particular form, now I can write it as a column matrix with just one index. I call this as sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6. So it becomes a 6 by 1 column matrix, right? So now similarly I can write my strain also using the Voigt notation, putting all the normal strains first and not really abnormal strains, but shear strains over here. It's funny, the English language, how sometimes ambiguity is there in terms of calling it normal. The word normal has so many meanings to it. When we say normal, we are talking of orthogonal or perpendicular over here, not in the sense of normal and abnormal, right? So these are not abnormal stresses, just that there is a distortion that is taking place. The reason why this is normal is the shape doesn't change. It's only the size changes when you have these three strains. Here the shape itself changes because you're essentially having a distortion, as we showed in this particular example, where two perpendicular lines are no longer perpendicular with each other, which is what is the shear strains, right? So once again you have a 6 by 1 column matrix. Now it's much clearer for us to see that what we had as 81 becoming 54, now becoming 36, because if I were to relate these two, then I should have a 6 by 6 matrix over here. Consisting of C11, C22, C33, C44, C55 and C66, right? And 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 and so on, right? Now we don't yet know that this is symmetric. If this was symmetric, then we get into what we called as the major symmetry before breaking for lunch. Here we said that I and J interchangeable is a minor symmetry, depends only on stress. K and L interchangeable is also a minor symmetry because it depends only on the strain. Now whether Ij can be interchanged with KL, that's a major symmetry which is still under question. So your Ij and KL, in other words, can I make Ij as the superscript and KL as the subscript? Okay, so that is a major symmetry if they were equal to each other, if they were interchangeable. Okay, I mean, it's a different matter that they're all dummy indices and therefore you can interchange in a different way, but I'm saying once you have fixed, can you interchange, which is what we are talking about in the sense of a symmetry over here. Okay, so the Voigt notation is to go from, all that it is doing is to go from a 3 by 3 stress and strain to, from which is essentially a square matrix. It's transforming that into a 6 by 1 stress and strain again, of course, which is a column matrix, exactly like the way we have done this, which means that now instead of your E I J K L has now got transformed into a C matrix of just let's say some Mn, right, where M and N vary from 1, 2 all the way up to 6, right? So it's essentially the same information that is contained in that, but in something that we can write on a 2 by 2 surface like this whiteboard or a piece of paper or on your computer screen. So essentially you're looking at something which can be displayed in a two-dimensional space. So that's the advantage of this. This has nothing to do with any new additional assumption that we are making. It's the same set of 3 assumptions that we have made, which have led to a smaller sized problem, what looks like a smaller sized problem, but in reality sigma continues to be a second order tensor, gamma continues to be a second order tensor, and the C actually is a fourth order tensor written innocuously as if it looks like a second order tensor over here, which it isn't. Okay, so it follows all the rules that fourth order tensors follow when put in an appropriate form, but we just taking that, extracting that information. So now the question is this symmetric? So that we have not yet come to. With the 3 assumptions that we have made already, this cannot be said, because if this is true, then we have a major symmetry in place. Okay, because then you see that your Ij and KL can be interchanged, because Ij is what shrunk to just a single subscript over here, and KL is what shrunk to a single subscript over here. Instead of going from 1 to 3, they are now going from 1 to 6. That's all that has happened over here. So now, in order to be able to make this simplification that it is symmetric, we have to introduce the 4th assumption, which is what we will do. Is there any question on this notation or any of the 3 assumptions that we already made in the morning? Okay, all good? Okay, the next thing that will help us to eventually get to the symmetry of this is what is known as the existence of strain energy density, so which I'll abbreviate as SED, strain energy density. Like we have been dealing with other kinds of densities like mass density is mass per unit volume. Here we are talking about energy per unit volume, which is the strain energy per unit volume. Okay, so which we will denote by the symbol. Maybe I'll erase part of the board. we'll call it as U3D, which is having the units of in SI units, the system, it will be joules per meter cube. Okay, so it's the energy per unit volume. That's what you're talking about, and it's very important concept, because later on we will see, even for our structural analysis of various components of the flight vehicle structure like spars, stringer, etc., or even the skin for that matter, we will introduce two other concepts very similarly, which is U2D, which is in joules per meter squared, which is the energy per unit area, and we will also introduce the concept of U1D, which is joules in joules per meter, which is the energy per unit length. Okay, so this is energy per unit volume, and in particular we are talking of the strain energy. So strain energy per unit area and strain energy per unit length. Okay, this is very useful when you're talking of the 3D body itself, which all bodies are. Then when you're dealing with plates and shells, this becomes useful, and this when you're dealing with beams, in which we include columns, rods, shafts, torsional shafts, etc., everything put together. For them, this particular notation will be useful, right? So now this is for a later day. Right now, today's class, we are focusing on just U3D, but I took the opportunity to show the parallel that exists from an arbitrarily shaped body to one which has one dimension very small compared to the other two dimension, and which has one dimension very large compared to the other two dimensions. In that case also we have something of a similar concept, just that the dimensionality is slightly different. Okay, so now let's get back to U3D. So what is this? So it's not something that we are unfamiliar with. You might have studied in high school essentially a single degree of freedom system with a spring mass, and when you plot this deflection of the mass, let's ignore gravity for now, or you can think of it horizontally with 8-on rollers. So then what we are essentially saying is that there is, as the mass comes down, there is some energy which gets stored in the spring. Okay, so that energy, which we used to write as half kx squared, where x is the deflection. So the more the deflection, the square of that is the energy that we are talking about. So that's essentially nothing but strain energy, because remember what exactly is a spring. A spring is essentially, depends on the construction, but essentially it's like a wire which is kind of coiled up, and then you're trying to extend that, so that's undergoing a certain strain. So it's in fact, from, if you look at it as the spring as a structural component, then it's a little more complicated behavior than just saying it's a linear spring with a spring constant k, okay, which is nothing but the constant of proportionality, whatever force you are applying over here. Okay, so that force with which you are pulling that force and the displacement x are related by a linear relationship, which is on a plot a straight line, and that's essentially given by F is equal to kx, right? And energy is nothing but force into displacement, which is the work done on this, assuming this is a conservative system and all the energy that you are expending by pulling this with a force F is all getting stored in the spring, which it's not, because there's some dissipation that is involved, but essentially that's what happens, and that is what is the area under this curve, because it's a triangle, because it's gradually loaded, it's not suddenly loaded, so it's gradually loaded, and therefore you see that the height of this is f and the distance is x, and therefore you end up with, when you substitute for f as kx, you end up with half the base into the height. half is here, the height is your kx, and the base is x. So you multiply half into kx into x, you end up with half kx squared. Okay. So now all that we are trying to do over here is to extend that to generic structures which have at each point there is essentially a strain that is building up. That's your strain energy density. So we are generalizing that concept of K over here and the concept of U that we had over there to your U3D, which is a density, which is a distribution now within the structure. Here it's for the entire spring, how much it is stored. And this is nothing but an example. So your strain energy is an example of another concept that you are very familiar with from high school, which is your potential energy. Okay. So you take a ball or any object and hold it at a certain height, it has a certain potential energy, and you drop it because of the gravity, it goes down. So its kinetic energy goes on increasing, and if you take that as the baseline or the datum, then you have come back to zero potential energy and maximum kinetic energy when it hits. So that's essentially when you again pull it up with some force external to the system, then you essentially give it a certain potential energies, right? So that's similarly what is happening over here. Whether you are extending or compressing it, you are ending up with putting it some strain energy. Now the beauty of this approach is that you are now dealing with a scalar quantity. Energy is a scalar quantity, unlike the stresses, strains, and the stiffnesses, etc. that you were dealing with earlier. Now you're dealing with a scalar quantity which doesn't have any direction. For example, instead of pulling it, if I were to push it, the spring will get compressed. If I push it by the same amount and it has the same spring constant both in the positive and the negative directions, then once again it will be half kx squared, because x will be negative, but a negative squared will still be positive, and that's essentially you're storing the strain energy once again in the spring, right? So same thing in the case of the strain energy density. In fact, the simplification, this particular way of going to the strain energy actually helps us to a large extent. But once again, the same issues are there, that it's not a fully conservative system. Just like there is some dissipation there can be some dissipation in that also because of material damping that is there and various other aspects that can be there associated with the material. But we'll ignore all of that for now, and it's a reasonably good approximation to start with, that your strain energy density can be purely defined in terms of, here we defined it in terms of a force. So where this actually came from is actually half, because we are gradually loading it, times F times X, right? And it's F that we replaced as Kx, and that's how we ended up with half Kx squared. So same thing over here, we can talk of now per unit volume. So therefore we talk of a stress and a strain instead of a force and a displacement. So this U3D is going to be given by 1/2 of your sigma I, let us say, going with the Voigt notation, where I can just give a single index from 1 to 6 into your gamma k, which is essentially your gamma 1 to gamma 6 that you see over here. I'm sorry. It's an implied summation that you're taking over all the i's that you are talking about, right? Now this sigma I, we already showed, is C times gamma, right? So I can put that in a matrix form. So essentially what you're talking about is C times gamma that you have multiplied by a gamma again. So that's essentially what you're talking about, right? So now you have something like that with, of course, the half factor that is there over there, right? So that therefore your U3D can be put in the simple form of Ij with Ij over there, right? So in other words, this is nothing but the force that is exerted, more in the sense of a stress, because it's force per unit area, and then that you're multiplying by the strain to get so not a displacement, but you're multiplying by a strain, which is nothing but the change in length multiplied by the length. So there is two lengths involved here, one length involved here, which is why you are getting per unit volume over here instead of the U that you have over here, which is in joules, okay, unlike this, which is in joules per meter cube. So that's essentially the existence of the strain energy density that we are talking about over here. Now, if you take the first derivative of this with respect to gamma j, then you end up with, because it's quadratic, it will, there will be a factor of 2 coming up, just like if you think of half kx squared, if you take a derivative, the 2 will get cancelled with half and it will just end up with kx. Similarly, here also you will end up with a Cij gamma I, which is nothing but this particular equation that you see over here, which is nothing but your sigma j, right? So your sigma j is therefore equal to the derivative of the energy with respect to the strain, which is very similar to what you are doing over here. The force is the derivative that you see over here. So if you take the first derivative, then you end up with the force for the energy. If you take the derivative, so the 2 and 2 get cancelled, it becomes kx, and kx is nothing but your force over here. And you take one more derivative with respect to x, you end up with k. So similarly here, if I take one more derivative, I end up with the stiffness here, which is not k but Cij, right? So if I want to take the second derivative of this, what I do is I take the derivative with respect to sigma I. So that is sigma j with respect to gamma I, and that becomes the second derivative here, rho squared u3d of dou divided by dou gamma I dou gamma j, and that's going to be your Cij, right? Now this is an important relationship that we have here, that if we know the expression for the energy, then we take the second derivative of the energy with respect to the strains, we end up with this stiffness matrix that we wanted to populate, right? But in reality, the way this is populated is not the way it is written over here, but the inverse of it, and we will see what that is very shortly. So then the performance of experiments becomes much more natural with that kind of a thing, whereas this way of writing it is very good for computational purposes. We'll come to that difference a little later once we finish with this fourth assumption. Now what does this fourth assumption say? That this exists, U3D exists. If U3D exists, then Cij is equal to this particular expression that is quite clear from this, and of course it already includes the other assumptions. It's not that we are separately looking at this alone. We have taken into account that it's elastic, which is why stress depends only on strain. Then we have taken the material linearity, which is why you see stress is a set of constants of proportionality times the strain. We have taken the no body moment, which is why we are dealing with sigma as only a column matrix of 6 by 1 rather than 9 by 1. So that's all taken into account. Now we bring in the strain energy density, and we are able to say that Cij is equal to the second derivative U3D with respect to sigma gamma I and gamma j. Now those of you are familiar with second derivatives with respect to two different variables, you know that it doesn't matter whether I first take the derivative with respect to gamma j and then with respect to gamma I, or the other way around. So in other words, this is same as from purely a mathematical this is equal to that. But if you look at that definition, then that is nothing but your Cji, not Cij, right? Now if these two are equal, obviously these two are equal too. So this equality is implying this equality, right? So the fact that the order of taking the second derivative does not matter. You can take with respect to one variable and then the second variable, or you can take with respect to the second variable and then the first variable. Then the derivative value doesn't change. Therefore, what it is defined as should also not change. The one is, in one case it is Cij, the other case it is Cji. And what does that mean? That the C matrix is symmetric if the indices of C are interchangeable, right? So therefore this question mark that we had now is no longer needed. and so we say yes, it is symmetric, right? But under the condition that the strain energy density exists, which is a reasonably good approximation. In fact, it's the truth, which is why it is in green, because even if there are dissipations, which there are in reality, a major part of it goes into the strain energy density, and you can actually account for the dissipations in an appropriate modeling way, because which is beyond the scope of an undergrad course, using material damping, etc., all other kinds of dissipation that might be there, because if it's in an environment where there is air damping and all that. So you take all of that into account, and then you can arrive at what is remaining as the strain energy density. But even in that case, you can end up showing that this particular symmetry holds, and which is what is the advantage of taking this strain energy density, which is what we had earlier called as the major symmetry. Because in the sense of C, you don't see that, but what C is actually is an E, which is having both two subscripts and two superscripts, and we are saying that if you put the subscripts as superscript and vice versa, you will not change the numerical value, which is what the major symmetry is all about, that the stress and strain are interchangeable, and therefore you end up with this particular simplicity. Now, how many constants do you have? You started off with 81, you went down to 54 by definition, you came down to 36 because of no body moments. Now that you have this major symmetry because of the existence of the strain energy density, that's the fourth approximation or assumption, how many constants do you have now? Independent constants. Okay. Exactly, yeah. How do you come up with that number? Yeah, yeah. That's correct, yeah. So you just counted it? Yeah, yeah, okay. So yeah, so that's the right approach, but a simpler way to do it is you have 6 by 6, so you have 36, of which 6 are diagonal terms. So you subtract 36 minus 6, you get number of off diagonal terms. Is equal to the total number of terms minus the number of diagonal terms, right? Principal diagonal terms. So that's your 36 minus 6, which is 30, right? And they are getting divided into top and bottom, so equal number. So which are on the above the principal diagonal are only 30 by 2, which is 15, right? So you have 15 off diagonal terms which are independent to deal with, and then you have 6 diagonal terms. So 15 plus 6 is 21, as Nafis rightly pointed out. So that's the number of constants we have now. So all the way from 81 we have come down to 21 because of these 4 assumptions that we have made. In fact, the second, third and fourth, because at this stage of first we didn't even have constants, it was all arbitrary nonlinear functions. So we have come down to 21 over here, right? So in terms of experiments, you need to do only 6 experiments, and some of those experiments you don't need to do as many measurements. Some of one first experiment you do 6 measurements, 5, 4, 3, 2, 1. Of course, you can make as many measurements for all of them and try to correlate and see if there are any issues and things like that with the experimental errors, etc., that you can overcome or try to cancel out. So all that is possible, but essentially the complication of the experiments actually comes down. But as I already told you, this particular equation, the way it is written, is very good for computational purposes but not for experimental purposes. The reason is, if I want to perform an experiment with this, let's say I want to populate, let's say, the first column over here, okay? There is C11, C12, C13 all the way up to C16. If I want to do that, the experiment that I have to perform is one in which I have to apply only a gamma 11 and keep all the others 0. If I want to keep all these others 0 and apply only that, the kind of boundary condition you can imagine, so if this is the specimen, all that I'm doing is trying to pull it with a gamma 11 over here, and I'm trying to pull it with a gamma 11, you already know that because of Poisson's effect there's going to be a gamma 22, there's going to be a gamma 33, and to restrict that and not allow gamma 22 and gamma 33 to take place, to keep it as 0, is very, very difficult. You can't really have any appropriate boundary conditions to do that. Okay. So similarly, in a general composite, all kinds of coupling exist, and you could even have the shears, which is the gamma 23, gamma 31, gamma 12, etc. inside it. It's very, very difficult to do an experiment where you keep only one of the strains non-zero and all the others as 0. So if you really want to do an experiment, you have to invert this particular matrix equation that we have written on the board, and then you have gammas in terms of the stresses sigma, right? So let's quickly write that out. Yeah.
So for the strain energy density, any particular reason why you superscript the strain?
Very good question. So this is exactly what we call as a contravariant basis vector. Okay. So it's actually slightly beyond the course. We can probably discuss separately. But what essentially you're having is there can be multiple basis vector systems for defining your problem. One is called as covariant, and from the name itself you can make out covariant. That is, it's varying, and it's varying along with something. So as I said, you can have coordinate systems where you have an axis, right? So these axes in a dextral triad, you have it as x1, x2, x3, right? But and straight lines. Now in a curvilinear coordinate system, they need not be making and it need not be orthogonal either, and each of these become curves. This is the x1 curve, x2 curve, and x3 curve. Okay. Now there is a basis vector which comes with each one of them, which is tangential to this curve. So if this is the x1 curve, I introduce a unit vector which is tangential to that, b1, which changes with x1, right? Similarly, a b2 which changes with x2, and a b3 which is a function of x3, right? Now these are called as covariant basis vectors, whereas you have that system now of basis which is varying along with the curves. Now in addition, you bring in the that system b1, b2, b3, you get an orthogonal to that, because that need not be an orthogonal system of unit vectors. It's just that they are non-collinear and non-coplanar. They are not all parallel to each other, and they are all not on the same plane. Okay, that's all that we are saying. Now when you have something like that, you introduce a new system called the contravariant, which is perpendicular to the covariant system. So with respect to b1 and b2, cross that, then you get a unit vector which you call as something else. Let's say a big B1, for example, right? Now that's big B1, big B2, big B3 now becomes your contravariant basis vectors. So the convention in tensorial notations is to write anything which is covariant as subscripts and anything which is contravariant as superscripts. Okay. So, but from your point of view at this stage and undergraduate level, it doesn't matter, because we're not going deeply into the tensorial aspects, and also we're not very rigorous about the notation. So you can as well write it as subscript, doesn't matter. But also from the point of view of the Einstein's summation convention, it's usually in the original form of it, it's only when the repetition is one as a superscript and the other as a subscript, then there is a summation. Okay, which is also why I and I, j and j, both are summed over their entire ranges, which in this case is 1 to 6. Okay, I think I answered that reasonably well. It's not fully satisfactory because I have to go through a lot of other tensorial concepts in order to introduce that. I try to explain it as much as is feasible, right? Now coming back, I was just erasing this to write the inverse form of that matrix equation that we already have. I already told you how this particular order is arrived at using the Voigt notation, where you go about the diagonal of the sigma matrix and then go on the top of diagonal terms, right? But there's another easy way mnemonic to remember this. This of course is quite clear. 1, 2 and 3, all the normal strains are stresses are written together. Same thing holds for the strain as well. Now then the second thing that we do is to come with the shear strains. It's usually this order that some people get confused, especially the beginners, and put it in a different way, in which case a lot of things can get a little more complicated than they need to be, right? So easy thing to remember is that the first term misses a 1. There's no 1 in it. There's no 2 in this. There's no 3 in this. So 1, 2 and 3 are missing from these three. So it's easy to remember 2, 3, 3, 1 and 1, 2. And since we have already made the no body moment assumption, it doesn't matter how you write it. You can write it either as sigma 2, 3 or 3, 2, doesn't matter. You can write it as sigma 3, 1 or 1, 3, doesn't matter. Sigma 1, 2 or 2, 1, it doesn't matter. But this particular order of in which I have written it, there is some cyclicity to it. In other words, if I start with 2, 3, I can change the 2 to 3, which is the next in the series, and after 3 again it's cyclic, so it goes to 1. So 1, 2, 3, 1, 2, 3 is the cycle that you see in the first subscript. Similarly, in the second subscript also, you start with a 3, the next one is 1, 2, 3. So 1, 2, 3 cyclicity is over there, okay, which is why I've written in this rather than as 1, 3 or 2, 1, etc., right? In which case, if I interchange, I have to interchange for all three. If I interchange for one of them, then that cyclicity will not be there. But it doesn't matter, because anyway, because of no body moments, those are all symmetric, and the sigma is symmetric, and therefore the off diagonal terms are matching each other at the respective positions. So now, when you have something like this, then you have this particular matrix, what we will write, just like we had a matrix which is C over here, C which is a 6 by 6 matrix. Here you will have S, which is a 6 by 6 matrix. And this is a funny part again in terms of history, how this has this symbolism is arisen, because here this another name for this particular thing is of course stiffness, whereas this is compliance. And you already see the irony of this, that we are using C to express the stiffness and S to express the compliance. Okay, it's somehow stuck on, and most books continue to do it. So to be consistent with anything that you might refer, we will use the same symbols. That S stiffness, S is not stiffness, but C is stiffness, and S is the compliance. Okay, just remember that, and they are just inverse of each other. So if you know one of them, you can get the other one just by inverting it, right? So it's a 6 by 6 matrix inversion that you have to do in order to get that, because both are essentially your 6 by 6 matrices relating either stress to strain or strain to stress respectively. Now I've left it empty and not rather than put just like this S11, S22, because as I said, this is very useful for all computational purposes. Whereas this is useful for all experimental purposes. I already told you why this is not very convenient for experimental purpose, because you cannot set up a boundary condition where you have only one strain at a time, the others being set to 0. On the other hand, you can have very easily a boundary condition where you can have one stress at a time and keep all the other stresses equal to 0. That's what exactly happens in a UTM, a universal testing machine. When you have a specimen and you're applying a load parallel to the length of the specimen, you're trying to pull that apart, right? So when you're trying to pull that apart, the stress that you're applying is sigma 11, and because these are free surfaces, there's no sigma 22, there's no sigma 23, there's no sigma 22 and sigma 33, the normal ones, because there's the deflection takes place in such a way that it remains stress free in those directions. That's what the Poisson's effect is, right? So these can continue to remain 0. So I can perform an experiment in which one by one I take one of the stress to be non-zero, or I put all the other stresses to 0. So the first experiment, first of such 6 experiments, a list of 6 experiments, I will take these 5 quantities to be zeros and apply only this, not equal to 0. Okay. When I do that, I can put strain gauges in order to measure these quantities, sigma 11, sigma 22, sigma 33, for all of which I need only one strain gauge, whereas to measure something like this, I will need a strain gauge rosette. Okay, so which is essentially 3 strain gauges which are not collinear with each other, but they are coplanar, and then based on their angles, their readings, we can always determine some of the other strains that we are not able to get otherwise, including the shear strains, which is what that is used for. So when we do that, then we get what are known as the engineering constants. So this compliance is directly related to what we call as the engineering constants. Of course, this is a terminology within structural analysis, because engineering constants in a broader sense could mean many, many different things. So in the subject of structural analysis, whenever we say engineering constants, we are referring to elements of this compliance matrix, because what exactly happens is that I am applying sigma 11, I keep on increasing the value of sigma 11, and I plot my gamma 11. So what I end up with is a gamma 11 plotted versus sigma 11. Okay, when I do that, I get various points, and as you would expect for small strains, you would end up with a straight line. Now what is the slope of this particular line, the way we have plotted it? I'm plotting the normal strain in the one direction versus the stress in the one direction. So in other words, I'm applying a stress along the length, and I'm measuring using a strain gauge which is pasted or epoxied glued onto this. I'm taking that reading. I'm getting, as I increase the load, different points at very small load to the largest load that I'm applying. I'm getting these points from the load cell, and from the strain gauge I'm taking these points, right? And joining them, I get a straight line. What is the slope of that line? Gamma 11 versus sigma 11. Young's modulus? Yeah? It's related to the Young's modulus, but it's not the Young's modulus. So can you take that hint? What would be the unit of the slope there? What is the unit of gamma 11? Any strain? See, strain is defined as change, normal strain is defined as change in length by unit length. So what is the dimension? Yeah, it's non-dimensional, right? So this is non-dimensional. This is sigma is any stress. Correct, right? And your Young's modulus that you just mentioned is also having the same unit, sigma, as sigma, right? So one is non-dimensional, the other is having a unit of Newton per meter squared, and therefore, and the slope obviously is related to that, but it's not exactly that, because see what we are plotting versus what. This is the input, sigma 11, because I know about the load cell, what I'm applying. I can calculate that stress, and for each of which I'm taking the readings of the strain gauge. This is the output. Okay, so unlike in this equation where the input was sigma gamma 11 and the output was sigma 11, here it is interchanged, right? So now what is the slope of this? What units will it have? If this is in Newton per meter squared and this is non-dimensional, what is the unit of the slope? Yeah, so it's the inverse of the units of the stress, which is meter squared per Newton, as you said. So that how is it related to the Young's modulus? You're right? Exactly. So 1 over what we will call as EL or E11, okay? So which is essentially along the longitudinal direction of the fiber. So if you remember, we discussed this schematic to start with, and in this schematic we said that along the fiber direction is our structural axis as well for the lowest ply over here, or the lowest lamina, and then you see that is the direction x1, which is also the longitudinal direction, which is a concept we introduced in micromechanics as well. Along the length is longitudinal, anything perpendicular to the length is transverse, L and T as the superscripts or subscripts that we typically use with that. So therefore this is 1 by EL. And so where do you think in this matrix that term will go? Yeah, so it's the first row, first column, right? So that's essentially your 1 by EL. So we have started populating the compliance matrix, which consists in terms of what are known as engineering constants. The first example of an engineering constant is EL. That same experiment where I am increasing my sigma 11, I can put a strain gauge not only in this direction, but I can put a strain gauge in the other two directions as well. In which case I can also read gamma 22 and gamma 33, right? So I can plot those as well. Now, do you think that curve, of course that will also be a straight line because we're dealing with material linearity throughout, but will that line, if I plot on the same set of axes, if I plot, this is gamma 11, we call this just as gamma, this is gamma 11. Now if I were to plot gamma 22, that will also be a straight line running through the origin, right? But will it go below this or above this? Typically for a material. So what is gamma 11? Yeah, I'm applying a load in this direction, so stress is in this direction, strain also in the same direction. That's what you have got there. Now we want to get the strain in the other directions for the same experiment. So I'm applying the same levels of sigma 11. Will this strain be larger or smaller? Yeah. So you get all these points corresponding to the same measurements, and you end up with a gamma 22, right? Now, if you're doing it in the so-called principal material directions, by which we mean parallel to the fiber and perpendicular to the fiber. Why they are principal material directions, we'll come to a little later. But right now, it suffices to say, as long as you have introduced coordinate systems which are parallel and perpendicular to the fiber, then you are in the principal material directions. Now we are just lucky that the lowest, the bottommost ply here and the topmost ply are ones in which the principal material directions are parallel to the structural axis, because along the length and along the width and along the thickness are directions which are either parallel to the fibers or perpendicular to the fibers in those two layers. But in the middle layers, where it's neither 0 degrees or 90 degrees but some angle in between, then you see that the principal material directions which are parallel or perpendicular to the fibers are all different from the structural axis, and therefore some kind of a transformation needs to take place. Okay, so now what we are plotting over here is for a laminate in which all the fibers are in one particular direction and they are parallel to the specimen's length. Okay, which is what we are trying to get to over here, which is your 1 by EL. Okay, so to take this example, I remove these three top layers and I do test only with the bottommost layer or more layers just like that, okay, which have all fibers parallel to the length. When I do that experiment and I'm putting strain gauges along this, that's measuring gamma 11. If I put a strain gauge along this, I'm measuring gamma 22. If I put a strain gauge along this, I'm measuring gamma 33, and those are what I'm plotting. How would gamma 33 look like? Will it be in between these two, or above, or below? How would gamma 33 look like? Remember, the specimen is not these three layers, but just the bottommost layer alone. Okay, how would the gamma 33 look like? Very good point. Why? Initial? Yeah. No, not that, but recognize what is 2 and 3. Okay, 1 is parallel to the fiber, 2 is, yeah, and 3 is also perpendicular. So both 2 and 3 happen to be directions perpendicular to the fiber, and therefore your gamma 22 or gamma 33, but for a few experimental reasons, might be slightly below or above, but for all practical purposes, they will be on the same line. So in other words, whatever you are getting as coefficient here, the same you will get as a coefficient here as well. Okay, but we will come to those things a little later. Right now we will distinguish these two as two separate things. We will call this as 1 by ET and 1 by, sorry, if we do a similar experiment there, but here it is minus mu TL by ET. Now remember the Poisson's ratio that I introduced earlier. In the case of isotropic materials, you don't need to put a subscript, but in the case of the any anisotropic material, including composites, you need to specify the directions, because Poisson's ratios in different directions are different. And as I mentioned, there are two subscripts for it. One is the input, the other is the output. Okay, so in this particular example that we are doing, we are I think it should be ULT, right? So here we have as the input, which is what we are applying, that's in the longitudinal direction. So that is your nu L. Okay, and then the output that we are measuring is in the transverse direction, which is your ET, right? So that's what we are doing. And then remember that the definition for your nu LT is the output strain, which is in this case gamma 22, and the input strain, which is gamma 11, with a negative sign when only sigma 11 is applied, which is what is the experiment that we are doing over here, right? So now we want to get gamma 22 in terms of sigma 11. Your gamma 11 itself is sigma 11 divided by EL, right? So if you look at that, then you see what is gamma 22. There will be a negative sign. There will also be nu LT, and this is in the denominator, so EL will go on top, so it will come down over there. So that's what you have over here, right? Is this clear, or should I explain it again? Yeah, it makes sense. Yeah, right. So because by definition Poisson's ratio is input first and output next. That is how the subscripts are. So input in this case is sigma 11, which is along the longitudinal direction, and that's the strain gamma 11. The other strain is gamma 22, and with a negative sign to make the Poisson's ratio positive for most materials. And therefore you are essentially taking gamma 11, which is already read from this, which is 1 by EL times sigma 11, which I can just write as sigma 11 by EL. So therefore that trips over, EL goes to the numerator. When you bring it this side, it goes to the denominator, and I also take the negative sign over there, so that I can get gamma 22 in terms of sigma 11, right? So that's how this particular thing gets populated. So similarly, your gamma 33, I can write it as nu LT prime by EL, and I'm using T prime just to distinguish it's the third direction compared to the second direction. But as Ivan already pointed out, they are one and the same because both are transverse directions, both being perpendicular to the fiber, and therefore it's the same quantity. Just for visually distinguishing each other, I'm calling one as this 2 direction as T and the 3 direction as T prime. Okay, so that's how you end up with that particular thing. So similarly, you can measure using, as I said, strain rosettes, which involve at least 3 strain gauges which are not collinear with each other, very close to each other, so they're measuring almost at the same point, and therefore you can get the shear strains as well, and then we can populate that. So right now let's not jump it, because we are going to introduce a few more approximations or assumptions, and then we will see some of these actually go to zero, so there's no point in actually dealing with them at this point. But for arbitrary direction of fibers like this, then you will have in general a fully populated matrix, and these will have certain meanings, and then we will get to it over there. So let's start with simpler things and then slowly add up the complications into what really is involved in a composite structure used for flight vehicles. So I think I pretty much covered this existence of strain energy density. So all that this will do. So the second experiment, of course, I will take only sigma 2 to non-zero, keep all the others as 0. So then I will get the second diagonal term 1 by ET. Similarly, a third experiment will give me 1 by ET prime, and so on and so forth. Okay, so I can get all these things put together. So I can get similarly a 1 by G, which is the shear modulus TT prime. I will get a 1 by G TL or LT, doesn't matter, and T prime, and here 1 by G TL. Okay, now what exactly goes into these, I'm not writing right now. Of course it is symmetric, there's no doubt about that, but some of these are actually going to go to 0, which is why I stopped writing. Maybe I just complete this, which is minus nu TT prime by ET. Okay, so now you see all the direct effects and all the Poisson's effects which you are familiar with even in metallic structures which are isotropic are included here, but in composites there can be a possibility of these becoming non-zero as well, whereas in the case of isotropic metals you will have all of these as zeros. But even in composites, when you have the principal material directions like what you have in the bottommost and the topmost layer over here, we will see that a whole bunch of these go to 0, and they are because of 2 sets of reasons, and we will come to that next. Are there any questions so far?
So is it GTT prime, GT prime?
GTT prime, T prime L, and TL. Okay, that just corresponds to this. If you look at this 2, 3, which is T and T prime, and 3 and 1, 3 is T prime, L is 1, and I can write it as GLT or GTL, doesn't matter. Whereas for Poisson's ratio, I have to be very careful of the order. Here I don't need to. So here I can write it as GLT or GTL, doesn't matter, which is essentially 1, 2 or 2, 1. Okay. So for a metal, this is all that will be non-zero. Okay. So everything else will go to 0. So shear will be driven only by the shear stresses. The shear strain will not occur if there is no shear stress, and that too in the same direction. So there will be no coupling between one shear stress and the other shear strain also. So sigma 2,3 only causes gamma 2,3. Sigma 3,1 causes only gamma 3,1. Sigma 1,2 causes only gamma 1,2. Okay, so in other words, all the 5 other terms in these 3 rows are zeros. Okay, and similarly, if you look at this first 3 rows, it's only a 3 by 3 matrix at the corner over here, which is a submatrix, which is having non-zero terms. There's a set of 3 by 3 zeros over here and a 3 by 3 set of zeros over here. So in other words, there's no coupling between normal and shear. Whenever there is shear stress, there is only the corresponding shear strain, not even normal strains. Similarly, the other way around, if I apply this normal stresses, then there will be no shear strains which are introduced, and that's why you get another set of zeros over here. So whereas the only couplings that exist are because of Poisson's ratio, and if Poisson's ratio happens to be 0, which is a possibility for some materials, like naturally, for example, for cork, which you use to close bottles, for example, that cork has a Poisson's ratio of approximately 0. So then you will not have these couplings as well. Everything will be a direct effect only. Okay, but for general materials where you have a non-zero Poisson's ratio, you will have these three couplings for sure, even in metals, even in isotropic materials, what to say of composites. And in composites, if you have these special kinds of layups, zeros or 90 degrees only, then you will see that once again this simplicity remains, but once you introduce other angles, you will get a fully populated matrix in general. But we will get to that once we introduce the other assumptions over here. So are there any questions so far? Okay, let's go. The next assumption that we have is what is known as orthotropy. Okay, you are familiar with isotropy, where you divided a word into two. Iso is the prefix, so iso means same, and tropy means direction, so same in all directions. Okay, anisotropy is not same in all directions, but in between these two extremes you have a situation called orthotropy, which means that there are three planes of symmetry. In other words, if I take any one of these layers, let's say the topmost layer, forget the bottom three layers, then I introduce a plane which is, see, I already said this is along x1, this is along x2, and x3 is upwards over here, right? So now if I cut this along any of these three planes, x1, x2, x2, x3, or x3, x1, that is a plane which is perpendicular to x1, which is the x2, x3 plane, or you see there is a symmetry about that. Similarly, if I cut right in between over here, which is the nothing but the x1, x2 plane, which is perpendicular to x3, that will also be symmetric about that. Similarly, if I cut in this particular direction, which is perpendicular to x2, that will also have a plane of symmetry. So in other words, there are three orthogonal planes of symmetry, and because these are orthogonal to each other, we call that as orthotropy. So what is this plane of symmetry? So essentially it means that if this particular hand that I'm showing over here is a plane of symmetry for this structure that I'm holding, so then what it means is whether I go in this direction or that direction, the property will be the same. So that's a plane of symmetry, which means that there is, in terms of transformation, there is a 180-degree rotation about a particular axis that you're having of that plane, and then the properties should not change. Okay, so for this we need to introduce a concept called the rotation matrix. Before we go to that, the engineering constants that we already identified over there, apart from EL, are your ET, your nu LT, the nu TT prime, and the GLT. Okay, the others can actually got from each other, because remember T and T prime are interchangeable. Okay, so these are the five very important properties that you need to remember for the directions in which the structural axis and the principal material directions are coinciding with each other. The reason why I have not written, for example, GTT prime is that in that plane we will see in the next assumption, that is assumption 6, there is an isotropy, what we call as transverse isotropy. Therefore, knowing ET and nu TT prime, I can actually get GTT prime. So we will show how that happens, so which is why I put only the independent ones over here. Right, let's come back to this approximation of orthotropy now. Okay. Now, if these are planes of orthotropy, then what it means is that there is a symmetry, because of which we'll have to go to what is known as a rotation matrix, which is a function of the angles that the structural axis and the axis that your principal material directions are with respect to each other. Okay, which with respect to the x1 axis, you could have theta 1, rotation about x1 would be theta 1, rotation about x2 would be theta 2, rotation about the x3 axis would be theta 3, to go to a different coordinate system. So this is in general, but now we are talking of just a 180-degree rotation, in which case the rotation matrix becomes very simple. So if you have a plane of symmetry, then we are talking about a rotation which is of this particular form. So it's almost like the identity matrix, which you know has only zeros in the off diagonal terms and ones in the diagonal term. But the only difference is that because you're going at 180 degrees and you want the property to remain the same, so you get a -1 over here, which is essentially nothing but your cos 0 or cos 180, which is -1, which is what you see over here, right? So that's what you're going to take, and you have to see that which are the tensors that you have to kind of manipulate. So now the tensor that we are manipulating is this C matrix or S matrix equivalently, it doesn't matter. Now if you want to manipulate this C matrix, you should know what order of tensor it is. So you remember that sigma is a second order tensor, gamma is a second order tensor, this is a fourth order tensor. So actually 4 powers of R will be involved. So if you're going to transform this C to get to a new direction, then you will have to multiply by R's on this side and R transpose on this particular side, and R transpose anyway for this simple example is same as R. Okay, so whereas if you're going to transform only stress or only a strain, then you just have R transpose CR. So this is good enough for second order tensors, and this is good enough for fourth order tensors. But we have already written C in the Voigt notation, because of thanks to this simplified notation, you can't directly apply it to see the way it is in this particular matrix, because remember this is a 6 by 6 matrix, these are 3 by 3 matrix, you can't even perform this matrix multiplication. So what really I'm talking about going in there is essentially your the original tensor that you're talking about, that is what has to come there, and this is a matrix equation. So you have any fourth order tensor, so let's say C4, and you have any second order tensor C2, which can be written in a particular set of bases, here 4 bases and 2 bases. Then for that you can perform that matrix manipulation, and then when you do that, you will show that these quantities 3 by 3 matrix over here will all go to zeros. Okay, and similarly you will show that this triangular set of numbers over here 4 4 4 5 4 6 etc., they also go to zeros. So all that you're doing is taking this multiplication in its original form, and then you're setting both to equal to each other, because it should be immune to rotation by 180 degree, because that's a plane of symmetry. If this is a plane of symmetry, the properties here, and when I turn 180 degree should be one and the same. Similarly, if this is a plane of symmetry, then I start here, I have to rotate by 180 degree, come up here, the properties should remain the same. So like that, there are 3 planes of symmetry, this one, and this one, okay, orthogonal to each other. So once I do all of that, I can very easily show that these are going to 0. There's also another way of showing the same thing, which I'll probably do in the in Wednesday's class, because I want to complete something else before that. So in that case, what you can do is, instead of using a mathematical procedure to do this, you can also use a physical explanation. So you can start with this, and show that what is driving what. For example, if I want to prove that C14 equal to 0, what is it relating? It's relating a sigma 11 to to gamma 23, because it's the first element and the fourth element. That's what C14 means. And the fourth element here is 2 gamma 23. So is it possible for sigma 11 to drive 2 gamma 23, and that because this is symmetric, that same C14 will appear here as well. So in other words, is it possible for tau 23 to drive a gamma 11? Okay, and you can use physical arguments to show that if this is the set of principal directions, material directions, that is at least one axis is parallel to the fiber, the other two are perpendicular to the fiber, then you will show that those are going to be equal to 0. So I will illustrate that with a few examples on Wednesday's class. For now, take it from me that either by using a mathematical argument like this or by using a physical argument, you end up with the same result, that there is no coupling between normal and shear on the one hand and between the different shears on the other hand, which is why this triangular set of numbers also goes to 0, and you end up with only the diagonal terms and the Poisson's terms, which are 3 in number on either side of the diagonal. Do you have any questions related to orthotropy, so we can move on to the next?
3 planes of symmetry.
Yeah.
Right? So like that can also technically have 3 planes of symmetry, or
Which one?
like that the picture.
Yeah, so if you're looking at the topmost, then the planes of symmetry are same as the structural planes, because I have introduced x1 along this, x2 along this, and x3 along the thickness, right? So now you see that you forget the bottom 3 layers. You just see that this particular plane is nothing but the x1 x3 plane. So now the x1 x3 plane is a plane of symmetry, because either you see this way, fibers are coming out. If you see other way, fibers are going out, right? So that's a plane of symmetry. Similarly, if I cut it this way, once again there's a plane of symmetry, okay, which is nothing but your x2 and x3 plane, okay, x2 x3 plane. Similarly, if I cut it into exactly half, okay, that's your x1 x2 plane, and that is also a plane of symmetry. So essentially we are saying that whenever there is a plane of symmetry, when there is a 180-degree rotation, and therefore the rotation matrix is this. So if I use it for the appropriate tensors, in which in our case it's a 4th order tensor, so multiplication by R transpose twice on the left and R twice on the right, then I end up with why it is so. Again, there is a mathematical proof for that. I just don't want to go through all those details right now. Okay, so now all that we are saying is that once there is a plane of symmetry, the properties should be the same in both directions. And when we set those two equal to 0, in other words, you take property in this direction as C, properties in this direction as C prime, you're equating the corresponding numbers. When you do that, you end up with these going to 0. Otherwise, it's not possible. So that's the mathematical way of proving that these are zeros. On the other hand, you can't do that with these two layers using the same set of axes. But you can introduce new sets of axes which are perpendicular to the fibers in those planes, and the same thing will hold. Okay, so depending upon this choice of axis and how it is oriented, a choice of structural axis and how it is oriented with respect to fibers in a particular layer, this may or may not hold good. Okay, so in all cases you can start with the principal material direction of the fiber and that particular ply, and then make a transformation to the structural axis to get the zeros actually populated with non-zero values because of the transformation that you have. So that transformation once again will be a transformation of this kind. It will involve, because here we got cos 180, so we put it as -1, but in general it will be cos thetas, cos theta 1, cos theta 2, cos theta 3 will be involved, and because each of them is linear in the cosines, but since you have 4 of them multiplying each other, you will have cos power 4, sin power 4, or sin cube cos, cos cube sin, sin squared cos squared kind of terms. So those, each of them will have different coefficients and they all get added up. So it's kind of a messy kind of a thing, but it's quite tractable using the kind of computational symbolic resources we have today. Any other questions on this before we get on to the next approximation, possibly the last for today? Okay. So the next one is what we call as transverse isotropy. Okay. So transverse isotropy is the fact that, once again, you have any plane which is perpendicular to the fiber is having all directions perpendicular to the fiber, right? So if this is a bunch of fibers that I take in a particular layer, I take a plane which is perpendicular to that bunch of fibers, whether it's this direction, or any direction in between, they're all perpendicular to the fiber, right? So in other words, the property in this direction, every other direction there should be equal to each other. When we say that in a three-dimensional sense, we deal with an isotropic material, okay? That properties in all directions are the same, we call it an isotropic material. But here it's not an isotropic material, it is an orthotropic material because it has three planes of symmetry. But now in that we have another simplification because of transverse isotropy, because it is a long fiber